So remember that the concept was that at this point we have explained how to develop the numerical tool that based from some inputs it creates outputs. Right? I detail geometry, I detail boundary conditions, I detail thermophysical properties, I detail everything. It gives me outputs. Temperature profile, heat loads, whatever. Okay? But now the interesting part is that if we link this to an optimization tool, then the inputs will be driven by the optimization and the outputs will be read by the optimization algorithm. And we will do this loop until we get sort of a minimum. Okay? So that's the concept behind. There are now sometimes the space that we need to explore in the inputs is huge. Like if you have only one input, then it's easy. It's the easiest part. So we have, this is the input and this is the output. And we want to minimize this output. Imagine this is cost and this is whatever, I don't know, any geometrical decision or in the design or whatever, the diameter or whatever you are designing. And that's the performance. So we want to minimize this and you have a function like that. Okay? What the optimizer will do is, okay, try input value 10. He runs the numerical model and gets this output. Now try 9. Tries 9. Oop, I'm in the wrong direction. He goes to the other direction now. Now try 8. Okay, we are in the good direction. Go further. Try 7, 5, until it gets worse, so it will converge. Right? So it's a trial error at the end. So the optimizer is asking and the model is solving. That's it. So try this. Okay. Try that. Okay. For 1D, for one variable problems, it's easy. It will always get something correct. But what happens if the function is like this? It might happen. Sometimes one single variable, it doesn't have a clear minimum, but it has suboptimal minimums. Then, if we are lucky and we start here, you will find the correct minimum. If you are not lucky and you start here, you will find a suboptimal minimum. And your solution will not be optimized. Okay? That's something you need to deal with. This is Hook-Gibbs optimization. So this searching, it's named Hook-Gibbs. And I will going to explain two different optimization algorithms. So the point is, I will tell you how the optimizer is asking one input and not others. So based on what is receiving, he will ask one input or other input. It's not random. Now, one thing to, what can we do to solve this? Any idea?
Change the input with the weight to move on the right.
But you don't know. When you click, you don't know the shape. Actually, you never know the shape.
Okay, but for exploring all the space,
yes,
there is some weight factors for the inputs.
Mm-hmm.
For exploring all the space.
Usually exploring all the space is not possible. It's not possible to explore all the possibilities. I mean, all the possibilities are infinite. Right? Because this is not, solution will be that input, the input that minimizes output, maybe is 23.48765. That is the solution. That is the solution. It's not 23.4. No, 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 no. The solution that minimizes is this one. We are not parameterizing here. We are not saying try 23, 24, 25, 26. No, 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 no. We are trying to get the minimum at a single resolution. But this is the minimum. So, any other idea, Yanis?
If we run the code several times in order to see if the result will be the same or it will be different, a different one.
If you do this one and again,
Yeah.
but we don't know. But are you going to do that in real life? I mean, when you do optimizer, you get one value and say, maybe not, try again. And get another value and say, no, try again. How many times are you going to ask? Until when you will say, okay, that will be the minimum. You don't know. Maybe you have 30 minimums in the curve. Maybe your curve is like this. How do you get that? Now, first thing is that you don't know for sure which curve do you have, but you can know more or less if this is like a fluctuating parameter or not. This you know. You can, because you know the physics behind, because you know the case study, because you are experts on that, you are doing research, you know more or less how it will go. If you think, okay, it's not going to be very clean, we'll have some trouble, then you can say, optimizer, instead of having one seed, one beginning, we start at 10. Okay, you start at 10, and then you have two seeds, two starting points. Start at 10 and start at 20, for example. Or start 4 seeds. And he will do the searching with these 4 new starting points. So I start here, 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 and here. And I run for the 4 cases. Now with the 4 solutions, I generate new 4 inputs. With the new 4 solutions, and that's how I move. This point will go this way. This point will go this way. This point will go, I don't know, this way probably. And this point will be this way. Once the 4th, they are in the same point, or they reach different minimums, we will compare. At the end, this and this will get here. And this will get here. We compare the different minimums, and the algorithm compare the different minimums, and say, okay, this is the one you are looking for.
But what if we can't decide on the inputs, the range?
How many? Usually, it decides randomly. You can control if you want. I leave it randomly. And at least, I add 4 seeds.
But what if there are, even after 4, there is another minimum which is far beyond reach of that range?
How long does the optimization work? Then you can ask, okay, 1 seed, how long does it take to converge? 10 minutes? Then put 20 seeds. 1 seed, how long does it take? 1 day? It depends. How heavy is the numerical model? Because for each seed, it will take a while. I mean, not a while. It will take some time. You will see it later on. And this is for one variable. Only one variable. In the example that we saw yesterday, I had 3 variables. Right? Melting temperature, hour at which we go out, hour at which we come back. So we are looking at the combination of the 3 variables. The point here is that sometimes, and again, it's the same between accuracy and resources. Sometimes you will not get the optimum, but you will get a good value anyway. I mean, you can stop, if you are here, maybe you stop here, because it was reasonable in terms of seeds. Okay, can you deal with this solution? Are you, or not? Or you need the best minimum. Again, it depends on what you are exploring. But in the case of my facade, or of the system, I really don't care if it's not exactly the optimum. How much will I increase the performance? 1%? Okay, that's a good solution, what it gains. Okay? That's one algorithm of solution, hook jibs. Now, the example of hook jibs.
Can I ask something?
Yes, please.
I haven't understand what exactly means a different starting point. I mean, how can I change? How could I change the starting point of?
The algorithm will select for you.
Yeah, but that means different initial conditions.
No, different inputs.
Different
Not initial conditions. Initial conditions of the model are what they are.
Okay, different inputs. So,
Like, let me have another example. In the 2D, maybe the concept is, now we are going to have one house with one window, okay? And we want to optimize height and width of the window, two variables. And what we want to minimize is heating and cooling demand. So I want to design best possible window in my building. Okay? I have a house with a window A and B. I develop one numerical model that, based on A and B, it gives me the money I need for heating and cooling. And I want to minimize this money, right? That's the path. The optimization will ask, try these A and B combinations. Of course, first thing, and it's important, I will limit the range of exploration of A and B. Meaning, if I'm having a window, maximum width of the window, how much is it? I don't know, 10 meters. So then A from 0 to 10, and B from 0 to 5, for example. I don't care. So you explore this possibility. A and B from 0 to 5 to 10. You have all this space to cover. And those are different possible designs. Correct? Okay. Now, running the model, or in reality we can have like depths, or here, for example, you have 100 euros, here you have 90 euros, 80 euros, and at the end we have two minimums. Okay? Everyone understands that? This is 45 euros, this minimum. And this is 35 euros. Now, how hook jibs work? Imagine I have one single point. I start wherever. You can control or leave it randomly where to start. But this is not the initial conditions of that. The initial conditions of that is 1st of January. And I will run all the year. But with this input, the input will be a standard window. For example, A0, B0 will be, I don't know, will be 2 meters by 1 meter. That will be the starting point. 2 meters, 1 meter. Here we are. Okay? So, what hook jibs will say is, I will run this case, I will have this case, this case, this case, and this case. Because it's in 2D, it will go forward, and back. Which is the best direction to go? That one, right? Because I compare the amount of money that I'm spending the whole year, and the best solution was to go this way, which is, this is A00, this will be, I don't know, A2 meters, and 2 meters probably, I don't know, right? In B, I'll go higher. This was 1, this was 2, This is 2. How about this? Now, do the same. Where do I advance? This is the way. Right? Now, do the same. Here, here, here. Which is the best? I am not improving. Correct? I am not improving. The best case was this one. So, reduce the length of the jump. Now, he will try this, this, and this. And this. So this is how hook jibs work. Clear? That? Now, if we have 2 seats, that means that we will have 0, 0, and we will have, for example, 5, 3. 5, 3. We will start here also. We have 2 different starting points. There and that. And this will do this cross, this will do this cross. Oh, this is going. And they will have different paths. Until it goes here. When both seats achieve convergence, it means it is not improving, then they will compare different minimums. Oh, this is 45 euros, this is 35. That's the best. This is your design. 8, 9.58, whatever, B, 0.85, 87, I don't know. This is your best design of the window. That minimizes heating and cooling of your building. Clear?
So,
Yanis.
if I get this straight, what we are doing is to run the same code with different inputs several times in order to have more chances to find the global minimum.
Correct. That's it. That's why it is very important to try to have the lighter numerical model you can. Because you will run a lot of times. It's not only, okay, my numerical model stays 30 minutes. I don't care if it's 30 minutes or 20 minutes. It cares. It does, because maybe you need to run 1,000 times. That's why I was I was saying a lot of time, so many times, try to reduce complexity in your models. Unless you need physics, don't add them. Unless you need complexity, don't add them. I know everything is 3D and transient. I know thermophysical properties are not constant. I know this. But if you can assume and you can simplify, then you can do this kind of tools. Otherwise, you cannot. Okay? Any question about that? So this is how hook jibs work. The second algorithm that we will see, and this is useful for, especially for 1D or 2D models. So we are not covering all the domain. I mean, we have not explored what happens here, or what happens here, or what happens here, for example. We have not explored, but we have done it in an ordered way. Right? We are picking 2 seats, or 4, or 5, or however, how many seats you want to start, but then everything is guided. The second one is genetic, is particle swarm. Genetic, it's very powerful, and it relies on Darwin at the end. It relies that the most capable survives and the others don't. How does particle swarm work? We start, let's say, usually you can define how many generations do you want to go and how many individuals you will born every generation. That means trials. In this case, if we apply particle swarm here, okay? If we apply particle swarm here, what is going to happen? Randomly, first generation, that means humans at the very beginning. Okay, whatever species at the very beginning. 20 points. 20 points. Run the simulation for these 20 points. And save what are the cost of these 20 points. Of these 20 guys trying, right? Now, from these 20, you can select the best 10, for example, they will be the fathers of the following generation. That's the main concept. The best 10 out of this generation, they will combine between them randomly and will generate the 20 new individuals. Okay? And we will do that during generation over generation. That means that if from these points, okay, this will survive, that will not survive, that will not survive, that will not survive, this will survive. Okay, that will not survive. For example, it survives this point, closer to the minimums. Now, the new generation that we are having, there will be children of those, of the best from the first generation. So, the second generation will be being born around. Now the same. Best 10 have kids. The other 10, bye-bye. So in this way, you will have solutions near the optimum. This is near the optimum. This is not this is not a tuning like before. It means that after a certain number of generations, you will have a value really close to the optimum, but not optimum. You will not be that lucky that the individual will be perfect for you. No, he will not be perfect, but he will be very good. Okay? This is the concept. Now, it is not true that from a generation of 20 people, we kill 10. What happens is, usually, you have 20. Usually the first, let's say, 5 go directly to the following generation. From 5 to 15, no. Let's make it. The best 3, if I have 20 individuals, usually the best 3, you can tune these parameters. The best 3 goes to the following generation. From 3 to 13, they reproduce. So we have new kids out of that. And from the following 7, 3 of them have also kids. And the other are discarded. Because it can happen that, imagine that the domain is huge, it can happen that the parents were not okay, but the kids results very good. So in this, if we are just selecting the best, we will be very dependent on the first distribution of individuals. This is an easy example, but imagine you have 4 variables, a 4D search. Then the space, the domain is very high. So it can happen that now for this particular point and this particular point, results are bad. Do we kill the parents? Okay, let's give them another chance. So, and here it's okay. Or it can compete, or it can reproduce with this other guy and have the one which is the best solution. Okay? So it is some random stuff, but you are guiding the survival process. So this is the concept of particle swarm, the genetic algorithms. That's why it's named genetic, because it's how we are here now. Okay? Yes.
How these best selected individuals reproduce? I mean, it's simply the mean of the
Well,
parameters.
you can control if it's the mean or randomly weighted.
It is the position in space, because they have velocity and memory each iteration. So I think you are searching in For example, for
Yeah, I mean, it's like a distance, weighted distance.
Weighted distance, usually the weighting between mother and father is random.
Okay.
It's something in between.
Because, for example, in your example, I mean, you have two minimum. Let's say, so I will have some individuals from that area, some other from this one. So if I'm gonna weight them, I'm gonna be in the middle where no minimum exists.
No, because at the end, those will be better than those ones. Sorry,
Okay.
those will be better than, so those
So
will
you
be
will have-
killed.
Okay.
Those will be killed. Because
I
those
mean-
were better.
You are not gonna.
I mean, the kids of these two will always be better than the kids from this to this or to this to this.
Ah,
So
okay.
they will, in generation number 6, they will be killed,
Later on.
for example.
Okay.
That's the principle. Okay? So, now, any question? It's clear, more or less? So, now before, okay, so optimization concept, what? No. Before we move to the example and I show you how to use Genome, link into the numerical tools, now I will show you how to do it with C models. But you can couple to any, Transys, Energy Plus, console, whatever model. It can generate a TXT file and read a TXT file. You can link with Genome. I don't care how you model. It can be even a function if you want. It can be whatever. If your model is able to read one TXT file, meaning, okay, this is your new command, and is able to produce one TXT, so we can communicate to that, all the models can do that. All the platforms. Console, Fluent, Transys, Modelica, MATLAB, everything can read one TXT and write one TXT. Okay? The example that I'm going to use today is coupled with C, because that's why I'm using it. But you can find ways to couple the Genome to any sort of numerical model. Now, very useful for scientists. Optimization is useful for optimizing design and optimizing control and validation. Now, sometimes, and the example that I'm going to show is this one. Sometimes you create a numerical model and you have experimental value and you are, you don't know heat transfer coefficient, for example, or you don't know a certain parameter. And you want to, and you are confident that the model is well structured and is giving reasonable outcome, reasonable results. So, yeah, this is a bit is recorded, but it's a good advice anyway. Now, for example, I'm thinking in a case in which the example that I'm going to show, it was a packet bed storage system, which means it was a tube of spherical balls of ice. Okay, it was ice. So that was a project with Professor Farid in New Zealand. That was for milk production, and it needs to chill the milk to 7 degrees very fastly to kill some bacteria or something. And so we have a given mass flow rate and a temperature, and we have the same mass flow rate with another temperature of the milk or of the water or whatever. So we charge first. We charge during night the cooling. We solidify all the spheres, and during the day we want to discharge this cooling. So we got the milk at 15 degrees, and we wanted to have at 7 here at the outlet. Okay, and imagine we are developing all this numerical model to get which is the best, depending on the temperature, which is the mass flow rate that I need to tune to get here 7 degrees, exact 7 degrees. Okay? I need that. That's why I needed the numerical model, for example. But I am not sure, and this is a very complex phenomenon, and the correlations are more or less, what was the heat transfer coefficient between the fluid and the spheres. How I developed that numerical model? That was a 2D model. What were the dimensions? Radius dimension and vertical dimension. Temperature depends on the position inside the ball, and the height, in which ball I am. I think that in the storage unit there were 30 spheres, so I got 30 nodes. 30 water nodes, and depending on in which node you are in one sphere or in another sphere. 2D. Right? How I did it? Okay, let's do one sphere if you want. Do you want or not? Or we can keep it. But it's the same. We have nodes like this. I equal to 0, I equal to n. All those has only conduction, this has convection to the water or milk flowing. The node of water is having two convections. One coming from the sphere, one leading to the cylinder, and massive term. Correct? It's the same as yesterday. Now, to compute the convection between the sphere and the fluid, it is tricky. There are some, I had the experimental values of temperature of milk at different positions. I put the model, and with the heat transfer coefficients available in the literature, they didn't concede. It was not correct. And I was trying. Okay, maybe heat transfer coefficient is giving to me, this natural correlation is giving to me 150 square meter Kelvin. I need more. I need more. It's because at the end the balls are not like this. In reality, the balls are like this. How I model that? So I changed heat transfer coefficient from correlations, and what I did, okay, I have the experimental values. It's a trick, but it was useful for validation. So now what I'm going to do is I have the model and the optimizer. And the optimizer will say, try different heat transfer coefficients. And the results will be deviation, standard deviation between experimental and numerical. Minimize this. Which heat transfer coefficient or which values inside the natural correlation minimizes the deviation between experimental and numerical. Because I was 100% sure that all the other physics in this are correct. There's nothing else. Conduction, I know the thermal conductivity of ice. Phase change, we have been using enthalpy method or equivalent heat capacity method for phase change. There's lots of publications out of that. Nusselt number in a cylinder surrounded by that's easy. There are plenty of correlations. But heat transfer coefficient between the spheres and fluid, that's challenging. That is something that is not very closed in the literature. There are some correlations. I tried all of them. All the correlations available. None of them was correct. None of them was numerical and experience show a good agreement. So I used optimization to, okay, I have a clue now. That's the best heat transfer coefficient that minimizes me the deviation. Then I have more information. Okay? Questions?
So, like, you mean to say that if I have a theoretical model or a proposed theoretical model which is which does not work, but I have
Theoretical or numerical?
Numerical,
Okay.
like a equation for some kind of reaction or
Yes.
some kind of process. But I have the experimental data which is robust and it has been confirmed. So I can, and I'm missing some kind of coefficient in the model. So can I use the experimental data and to get the coefficient or modify the equation at the end?
Up to you.
You-
This is one tool, extra tool you can use. If you rely 100% on your equation, and you can test with different experimental conditions, and tell me, okay, that coefficient was that one, and it gets the same minimum with different experiments. That shows that the coefficient was correctly.
Because I have an experimental data and then I want to generate a numerical analytical graph based on that experimental data, because the experimental data has some gaps. So in order to do that, I need to modify the equations at some point for coefficients in the equation. So that can be achieved by this.
Yeah, but be careful. You cannot state that your equation was correct, because you have tuned some parameters to coincident with your experiment.
Okay.
Like, if you are 100% your equation is correct and you can justify that your equation was correct based on other things, then you can modify parameters. But what you cannot say, okay, I'm inventing this equation, and yeah, this is coincident with the experiment. Yeah, this is coincident because you have forced to be coincident. This is trick. This is cheating, right?
Yeah, I have a relationship, but I don't know a certain coefficient in that relationship. So
I mean, case by case, it has to be analyzed. I am not saying you
but is it feasible?
it's feasible, yes. But it has to be fundamented in physics that they are,
Yeah, it has to be verified theoretically.
yes. And or also in the areas in which you have experimental data, yeah, you have this, or other experiments, it's the same coefficient, okay. That means that the equation is following the reality, okay? So you can optimize variables, but also it can help you to minimize errors when you are figuring out thermophysical properties or something like that, that maybe you don't have, okay? Or have an idea. Now, well, that's a long story, right? Now I show you how to couple both systems, okay? You have this in the email, okay? So that is the program that minimizes the, sorry, that the optimizer is like this. So I recommend you to, so you have this in the email. If you go to example coupling ice thermal energy storage unit, is this case. You will see the model here. You can have a look if you want. The point is that the file will read a txt file which is named x. I will read, and I will put that value in variable named v. Okay. The optimizer will generate one txt with a single value, which will be the H, the heat transfer coefficient between water and or milk and spheres. That's how I'm saying the numerical model has to read this value. Okay. Then V. So this is the model. I give it to you, and I say heat transfer coefficient is V. That's what it is. Then I run, and at the end of the code, I say, okay, now open one file to write, and the writing will be named f.txt. That's the f. Okay? And that's it. So I only preparing the model to be able to read one txt file and to write one txt file, nothing else. Now, you need all those files to run the optimization. This is X, txt file. We start with 1, for example. We don't care. Okay? This txt file will be modifying every iteration. F is the txt file that the model is generating as a response. Whatever. Now, there are 3 important files. First is the command. If I use the command, I say, okay, vary the parameter, which the name is v, from a minimum of 0 to a maximum of 500, and start from 200. Okay? Now you can select 2 different algorithms of solution: particle swarm or hook jeeps. You can see that particle swarm is commented. That means I'm running hook jeeps. Okay? So this is not executed. You see, it's between asterisk and dash, asterisk and dash. I don't delete it because then you have it in case you want to use particle swarm. But here, particle swarm, you have how many generations do you want to do? 20 generations. How many seeds per generation? 1. How many particles per generation? 20. So this was how particle swarm, you can control a little bit. Yeah, velocity gain, and then those parameters in which I'm not expert. To be honest with you, I'm not expert with that. I'm a user. Okay? Then hook jeeps. Number of initial points, 2. We start with 2, but you can start of how many seeds you want. Huh? Number of reproductions, 4. Okay? So it depends. You can control, and you can read on hook jeeps, you can read on particle swarm if you want. So this is how let's say, this is the settings of the search. And the most important part is this one. You say, okay, search v value from 0 to 500 and start from 200. Okay? Nothing else in this. Okay. What is in the bash simulation c.cfg? Again, it's the same as C. You have this. If you want to need it, if you need and you want to use it, just modify this, because that works. Modify this, and it will work. Okay? So if the variable doesn't vary between 0 and 500, if you have more variables, add them. There, that's it. Now, open that in... here is where I'm saying, okay, the numerical model, where is the direction of the numerical model you will run? Execute in the same folder, that means the same folder, in where you are. That's why I'm adding everything in the same folder. The optimization algorithm and the numerical model. You see that it's here. It was here. Everything was in the folder, example coupling ice test unit. Everything was here. The model, the exe file of the model, because you will not execute .c file. You will execute .exe file. Correct? .c, you need to compile .c. And then once you compile the .c, it generates .exe. Imagine, I delete the file. Now I don't have exe. I open the console, I compile. Now it has generated. Now, 1056. You need to compile your code. I mean, your code is not a program. Your code can generate a program. Okay? Now, in the bash simulation C, you say, okay, the executable of the, you need to say to the optimizer where is the direction of this program. It's in the same file, and the name is model dash, under whatever, v1.exe. Okay? Nothing else here. Last, of Linux. If you open that, I would recommend you not to touch with that, because here you say, the way in which I will communicate from here to that, that's the template of X. The file you will use as input, its name txt, x.txt. The file as output is f.txt. If you don't change that, it will work. If you, input, I want to say input, okay, then you have to change here input and play a little bit. But now it works. Okay? And that's it, and you have to deal with command.txt file. That's it, nothing else. Now, I'll run. I open Genot. Sorry, I have it already. Okay. I think it's in the desktop. PG course, eyes, covering eyes. So that's the optimal linux.ini. I start. He's doing first shot, the error was 1.1. Second shot, 1.17. He's trying. He's trying different v values to minimize f. Remember that in my model, at the end I said, well, at the end I calculated the error and write the error in the f file, right? So now Genot is looking to different values of heat transfer coefficient that minimizes the deviation. And it will go. So we have been 13 at this point, 14 simulations. So the model is very fast. Even being 2D, and its time was a couple of hours, I think. So it's fast, but it's taking a while. Now it seems it's stabilizing. So solution will be around 300-400, something like that. You see, it hasn't explored this area. V was from 200, he went up and said, whoa, this was okay. So he kept moving. So what happens if the minimum is here? We are losing that optimum then. Now, he tried, I put it 2 seats. One seat was at 200, the other one was here, I think, randomly at 400. Now, he will converge. If I see this picture, I can see, yes, I'm not exploring this area. So I will generate another seed probably. Because of the physics, I know that the heat transfer coefficient will not be below. And because I know from physics. But if you don't have a clue, then you need to force that the first seed is here, second is around here, and third is around here, probably. I didn't do it because I didn't need it. Now it's getting so now, if you see here, it's okay, iteration step did not reduce the cost, not reduce the cost, not reduce the cost, yeah, minimum cost obtained for this point was this. Point number 2, further decrease the cost, so he's looking. This way? No, it's not reducing, go this other way. Yeah, this is reducing, okay, go. So this is how it's going. When it's finished, was there or not?
I guess it's finished because it's screened the button.
Ah, yes, okay. Ah, yeah. Minimum 1.1. That's the minimum deviation. So, the accuracy that I give to him was reached. That means that, now, I close. In the same folder, you will have a txt file named output listing. If you open that, you have all the work that has been done by the simulator, by the optimizer. He has tried 200, and the output was 1.19. He has tried 210, and that was the output. So those are what he has tried, and those are what he got. And the minimum point was 372.5. Because my accuracy was 1 decimal. Do I need more decimals for heat transfer coefficient? No. If I say, no, instead of 1 decimal, I need 10 decimals, he will start working for nothing. Okay? So that was an example. Clear? More or less? Okay. Now, important topics. Let's do it again. So I will show you this trick. It took me like 3 days to realize this, but if I'm executing again, you can see that it is being generated a new folder with the 3 run, 4 run, is changing. So genopt is running inside this folder, right? So it is executing the model in the folder. Now what happens? That my model needs to read these txt files, which are the temperature from the experiments. Correct? But because they are running inside this folder, when I am reading from my C, from my model, I have to say that the files are not in the same folder, but in the previous one. So, I'll show you. I had some data to get. Like, imagine you need to charge weather conditions, solar radiation, whatever, txt, and you have this txt in one folder. Even if you put the model in the same folder, running genopt will create a new folder, you've seen it, and execute genopt inside this folder. So that means that when reading, for example, inlet temperature, or inlet mass flow, whatever it is, the location of this file is not in the same folder, but in the previous. That's why there are two dots here. Everybody understands that? Otherwise, he will go, genopt creates a new folder, but in this new folder, there is no inlet txt file. So the C software cannot find it. Unless I say, look for this txt file in the previous folder. Ah, yes, in the previous folder it is. Because I created a new folder. Right? So if I go here, I have the folder, inlet. Yeah, inlet is here. What the executable has to read is here. What happens is that if I run genopt creates a new folder. And it's being executed inside. And inside, it is not inlet. So it will not find inlet unless I told the code that you need to read the file which is in the folder behind you. Okay? That's trick. But again, I was running and it was giving me stupid things because he was not able to read inlet. And I didn't understand why until I realized it was creating this folder. So I lost 3-4 days looking for that. Now, and that's it. This is how it works. If I want, I can show you the model of the system, the system I told you yesterday, with 3 variables. It's the same. Let's open it. I think this one. Yeah. That will read each TXT file, and in the TXT file there will be 3 values. Temperature of PCM, hour to start, hour to end. Okay? I read this X file. That's it. And at the end, I am computing the load, I mean the amount of batch hour that is crossing over a period, and I am putting this value to F. So inlet was temperature of PCM, hour start, hour end, and output was load. Okay? And the structure is the same. If I go to command, now I have 3 parameters. 2 of them were continuous, another one I put it in a parametric way. Because I will not be able to decide PCM temperature 27.567. I cannot, I mean, PCMs are what they are available. So I said explore integer values of PCM, but explore the hour to go out from 0 to 24, explore the hour to come back from 0 to 24, and you can start going out at 12 night and coming back at 8. You can start here. Okay. Now let's see if I don't know if it's because I played a lot with that issue. Here in this case, I was commenting who gives, because there were 3 variables. Who gives starts to struggle. So I did particle swarm of how many, of 20 generations and 20 number of particles each generation. Results were, as I showed you yesterday, like this. He has tried to, with this temperature of PCM, hour to come back at 9 in the evening, hour to go inside at 5. That was the result. And after a lot of trying, you see, you have first generation. Now, second generation. Those points, most of them are keeps from the first. Third, fourth, until 20th generation. And got the minimum point that has been searched. This is not optimum. Maybe it's not optimum. I don't care. It's enough. Okay. If I let me see if it works. Probably not, because they are because I coupled 2 crazy things. But let me check. It doesn't work because what happens here is that I prepare the software for do one optimization in case we have 100% of PCM in the layer that is moving, in case of 75%, in case of 50, in case of 25, and 0. And when I create is a BAT file. I don't know if you know BAT files. BAT files are files that are executing the command console of Windows. So instead of saying do the optimization of 100, do the optimization of 75, I created a file that, this is out of the course, This is not useful enough for now. I created this kind of files, which are nightmares, to be honest. I cannot even open it. Anyway, forget about that. It's okay. So, do you have any question about how the optimizer and the numerical model are communicating and working? No? Clear? Okay. So, now, I wanted to talk about the heat, but just to justify my stay here, but since it's in the agenda, maybe we can skip, because it's very specific for building stuff, and I don't know if all of you are working in buildings, probably not. And unless you have something in mind after these 4 days, that you think, okay, I have this problem, how we can discretize, how we can apply the physics, we can combine them all together, otherwise we're finished.
I don't know if it's like exactly the case, but the issue that I want to discretize is it is a 1D model, 1D surface, but the physics in that is different from heat transfer. It's mostly mass transport, and there's an accumulation, and then there's a diffusion. So and it changes. All of the parameters like heat and diffusivity should be same across the material, but the availability of the initial parameter is reducing. Like it changes as it goes forward.
But you can assume that a part of the space is at the same velocity profile, for example.
Okay. And the accumulation is due to formation, and that like it's a reaction. Suppose oxygen is going into a metal, and then the oxide is forming.
Yes, you can put it in a you can do mass conservation, right?
Okay.
Mass in, mass out, plus mass generated, right?
Yeah,
You can.
and that accumulation, I don't know how to put a limit to it, because there will be a saturation point in that.
But that depends on the physics. I'm not expert on this kind of. So I don't know the equations you have to add. The point is that you can use this kind of methodology if you think that in your domain, you can split your domain into areas with the same properties. In this case, was temperature. But in your case, it can be velocity or density. Can you split your domain into areas with same velocity and density?
I can split my domain into a same density,
Yes?
exact same density composition.
Okay?
Just the concentration of oxygen changes, that is, as the depth increases.
Yeah, okay, but the point of discretization is that you are assuming that a certain volume, let's say every node, has the same properties.
Yeah.
Important to you.
Yeah.
In my case, the important part was temperature, but in your case, will be concentration of oxygen, for example.
Yeah.
Okay, but all diffusion has the same concentration of oxygen.
Yes.
Then, can you calculate the following concentration of oxygen based on boundaries and previous time step and neighbors? Yes. Then you can apply this method.
Yeah, because I know the initial concentration and I know the
Why it evolves.
Yeah.
Then it's doable. I mean, this is finite volume. Finite volumes are used now. The formations and so on, they are using finite elements. That's another story. But finite volumes have been used for fluids and for this for from the 80s. So this is nothing new. I mean, Fluent used that, but in another. The good part of Fluent, or I think Console uses finite elements, but Fluent ANSYS, the good part is that you can use unstructured grids. In our case, our limitation is that we have to deal with geometries in which you can structure the grid in an ordered way, because I need to be able to say to the computer, okay, you are here, or you are here, you are here. Like, if we are in a fin, one single index guides me where am I in the fin. But if I am in a car, how I discretize a car. If I am in a, I don't know, whatever, camera, if I am this camera, I'm trying to discretize this camera, the geometry is so complex that it's very difficult to identify the different nodes just using index. And that's why CFD has powerful, it's very powerful. Not only because of the equations behind, not only because of the solvers, but because of the mesh generators that they develop. In which, if you have whatever, now even if I have this solid, how I structure the grid based on what we have done? Difficult. Because the nodes, they are not even spheres, they are not cylinders, they are not squared. How I, now, Fluent will say, okay, you have, it will start doing hexagons and so on, and putting different nodes. Okay, I cannot do that. We cannot do that. The way we can implement into C, or at least I don't know how to do it. If I need to do that, I will go to the CFD, apply basic equations, but using its mesh solvers for mesh. If I need to do that, I will say, is acceptable to say this? That's what I would do. Okay? So there are kind of problems that you can model using what we have been discussing this week, and there are problems in which you need to find other ways. Okay? So, anything else? No? Thank you then. That's it.
May I ask just to present like 5 minutes the Reheat project so they all are aware?
Yeah?
Because in January it's also a call that may be of interest for you. Basically, Alvaro got one of these Marie Curie co-found call, which is for individual scientists that are basically in contact with institutions from other countries than, in his case, other from Spain. And they have this chance, which is co-found, which means that their local government puts at their disposal an extra fund that is typically joined together with the European Commission fund by Marie Curie program, and therefore it supports, let's say, their scientific work and salary basically for a couple of years. So it's something that you should be interested in, let's say, after your PhD and so on.
Okay, before, I will show you because I have this presentation. We can stop recording, right?
As you
Yeah. This presentation was slightly.
Okay. We can cut.
Okay.
Okay.
This presentation was for dissemination activities. We did some events with society. So people came from the streets to wait for the picture. I will. Wait.
So.
This one. So actually that presentation was made for communication activities. Now you are in PhD. So lucky you don't have to do this. But at some point of your research career, you will need to start doing communication and all these stuff, which sometimes is nice, but sometimes you are speaking to 3 people and saying, okay, I'm here Friday afternoon speaking to my father that came and 2 more, okay? But anyway, I think even it's out of a Refit project and so on, I always start my speeches of research justifying why we need research. And usually I show different maps, which I think maybe you are interested. You are interested. So first thing I show is how bad are in Europe regarding natural resources. Here are people, India, Greece, Turkey, but then Italy, Brazil, and Spain. So and Greece, yes. Except India, all the others are poor. Maybe Turkey, maybe you have something, I don't know. In terms of natural resources. Here, if we go to Europe, we have some copper in the south of Spain, which is false. We don't have anymore. Romans, you get all the silver, gold, and copper available in Spain. They say we have uranium, and they say we have oil in the sea between Scotland and Norway, which is not active now because of prices of oil. Some periods of the year it's closed because it's you need more money to get the oil than the money that it's in the oil, so it's not always open. So this is not very, it cannot be compared to those ones, for example. And regarding uranium, let's see how much uranium do we have. Here is another world map in which we have resources by country: soil, water, silver, corn, cotton, oil, gold, uranium, wheat, natural gas, rice, rubber, diamonds. And it's saying, for example, in the case of uranium, the previous map says in Europe we had some uranium. Okay, 23% of uranium is in Canada, 21% is in Australia, 16% is in Kazakhstan, 8% is in Russia, 8% is in Niger. No European countries here. Even there is no single point in any European country. So we don't have anything of that. Nothing. Neither water, corn, nothing. We need to import everything. So we are poor. Second message I give to people is, okay, we are poor, but maybe we are a lot of people. Yeah, we are not a lot of people. We are very concentrated, especially in Germany and so on, but this is a world map that in which each cell is 1 million people. You see India, 1.3 billion, right? China, 1.4 billion. All Europe, 700 million. So we are not so many. We are 10th% of population in the world, and we are very dense, and we are poor, and we are old in comparison to Asia, for example, or Africa. We are old, and we are rich. How? This is income, average income per person, sorry. Blue areas, more than $12,000 per year. Low income, less than 1. And in the middle, whatever. So, we don't have resources. We are few people concentrated in a region, and we have high expectancies. We have iPhones, we have car, flats, we have everything. So then people get a lot of worry. They say, wow, the future is bad. What can we do? Then I say, okay, apart, I'm talking about climatic change. So if people that are not even worried, then I talk about climatic change, then I justify why we need research. Okay? And then I start with my project. And they say, okay, I needed that. Take my money and solve the problems, okay? Then talking a little bit about that, and then I talk about the HIP. So basically, the HIP project is for retrofitting of buildings. We are trying to, you all know probably, that the building sector is consuming huge amount of energy. 32% is transport, 25% industry, 40% is buildings, and half of this 40% is basically for space heating and cooling. So that means if we can reduce the amount of energy that is spent in the world for space heating and cooling, we are doing huge advance in what is coming, right? Basically, the HIP project started to deal, or the first aim was to help architects and engineers to do decisions in the retrofitting process of a historical building. But then we realized that why should we focus on historical buildings? So we are developing an app that will be able to help architects and engineers in the decision of any sort of building that you want to retrofit. Maybe it is historical, maybe it is not historical. Historical is if it's defined as those buildings that are built before the Second World War, okay? And they can be whatever, churches, Palace of Westminster, office buildings, apartment buildings, office buildings. There are plenty of buildings that can be retrofitted, even being historical or not. So basically, the money of the project came from this funding that Alvaro was saying, the Centennial Spring project from Marie Curie grant. The team, we have UDL, we have you, we have architects in Lleida and engineers from Lleida. And the idea was to develop an app so architects can choose the best way to improve a building in 2 steps, passively and active systems. So the idea is that the engineer or architect will say to me, okay, this is my building with these characteristics, and this is my heating and cooling requirements. I want to be at 20 degrees in winter and at 24 in summer during this period of hours and so on. Based on that, we will run Energy Plus, and based on these inputs, I will tell you, okay, your building will consume this energy. You will need this amount of energy, which means this amount of money, to maintain this comfort, this level of comfort you want. Now, I propose you a different set of actuations to improve your building. So now we are exploring 600 possible combinations of improvements, meaning change windows, change insulation, add whatever, okay? So there are 600. We run the 600 models of Energy Plus. Everything with a cost associated, meaning that the engineer or the architect will tell me, okay, I want to improve this building and I have, I don't know, €500,000 euros, for example. What should I do with €500,000 euros? What is the best way? Okay, maybe the best way is to change the windows from the north, add insulation in the roof, and buy a biomass boiler. Maybe that's the best solution. There are also optimizers behind all this project, because sometimes we cannot explore everything, and we have to see. Okay. So the basically is we can improve the building in passive, and also once you have the different demands, how I reach these demands with a heat pump, with a geothermal heat pump, with a boiler, with radiators, with radiant floor. How? That's a cost associated to this actuation. That's a cost associated to actuation to the building. And the sum of those two shouldn't overpass the money that the architect has. So the idea is that everything is automatic. So the strength of the project is that we want to do this automatic. So the business will be that we will develop an app in which the architect sends me the information of the building. We are developing a software that is able to create the model without any human interaction, and after 1 day, for example, we will send you an email with, okay, this is the 3 best cases you need to explore. So this is like a pre-audit. And I will charge you, I don't know, 100 euros for this information. It will save you a lot of time. It will save you a lot of working hours of people in your office. And we haven't spent anything, just computing time. So this is an example of how numerical model help us to put this now here for decision making, for example. Okay? So this is Regi project. Okay, and we have this good logo.
Yeah.
I didn't do it.
The architect.
No. We pay the guy who is doing the website.
Okay.
He could do that. Okay? So thank you for your attendance to this. So you are the winners of the Hunger Games.